Welcome everyone to the February edition of our AstroCheminar. We have a great slate of talks today and some good discussions. Also want to mention that next month we have Sami El-Shal from Virginia Commonwealth who will be doing a presentation in our AstroCheminar for the March meeting, for the March session that we have. Today we have two wonderful talks from people that I have been fortunate to work with. So first today, we have Sarah Nickerson, who is currently at the NASA Ames Research Center. And she's going to be talking about the first mid-infrared detections of HNC and carbon-13 version in the interstellar medium. Sarah is originally born and raised in Canada. She got her bachelor's degree in physics and astronomy at the University of Toronto, then got a master's in astrophysics at McMaster before she jumped all the way across the pond to then do her PhD at the University of Zurich. She's now based in the United States at the Ames Research Center, and she is working on molecular observations of the interstellar medium and is bringing computational methods to process astrophysical spectral data. Alongside her advisor, Dr. Naseem Rangwala, she is building a molecular inventory of the Orion Hot Core with high-resolution spectra taken by the XCES instrument on board SOFIA. And I think we're going to hear some of those things today. So Sarah, go ahead and take it away.
Perfect. Thank you very much. All right, let me start the sharing. And I'm guessing this works for you. You can see everything fine. All right. So thank you very much for the organizers for this opportunity. And also thanks to my wonderful colleagues, a number of whom are here. And Tim, you'll also be hearing from after me. This work is a very interdisciplinary work that requires a lot of expertise from different fields of astronomy. And so I want to present to you today some exciting results we found using the XCES instrument aboard the SOFIA aircraft, and more importantly, finding two new species in the mid-infrared and the interstellar medium. And the objects that we are interested in are hot molecular cores. And these are very warm, small, and dense regions of gas that are associated with high mass star formation. And so this is really looking at an intermediate period where before you have the cold molecular cloud that forms the star, afterwards you have the hot ionized gas. And in between you have this stage where the radiation from the young protostar begins to heat up the molecules around it, and this leads to a very chemically rich reservoir full of a lot of molecules that we can study. And so far about 35 of them have been discovered in the Milky Way, maybe more. That's as many as I could count from literature. And excitingly, recently, about 4 extragalactic ones have recently been discovered in the LMC. The hot core that's the focus of our particular research is the Orion Hot Core. And this was the first hot core ever discovered, but despite this, it's atypical for a hot core in that hot cores usually surround the high mass protostar, whereas this one doesn't have an internal heat source. Instead, there's likely a nearby infrared dark but radio bright source I that we think is associated with the hot core. And the reason for the unusualness in this region is also likely because there's an explosive event about 500 years ago. And you can see in this image at the shorter wavelengths, the larger image, there's the explosion. You can see the iron and molecular hydrogen blown away. And then in the zoomed image is Orion IRC2, which is bright at 12 microns in the green. That is at the heart of this explosive region. And so previous observations in the mid-infrared of the Orion Hot Core done with ISO did reveal a lot of rich chemistry. a lot of CO, molecular hydrogen, acetylene, etc. But because of the lower spectral resolution of ISO, they could only identify the strongest features. And so now more recently, using the ground-based TEXEs, which is similar to XEs, it's a spectrograph usually used on Mauna Kea. And so this can now resolve the individual transitions of the molecules, but because it's ground-based, you cannot access the regions of the mid-infrared with heavy atmospheric interference. And so this is where SOFIA XEs comes into play. Because it's on the aircraft, it can fly above a lot of the interference from the atmosphere and complement TEXEs by taking observations in the regions that are most heavily affected. And currently, XEs is the only spectrograph that can access so much of the mid-infrared and still resolve the individual transitions. Even the James Webb Space Telescope will not be able to do this, though because it's in space, of course, it will be able to look at everything without any atmosphere and will be more sensitive. And for our research, we use XEs to look at conducting an unbiased survey from about 7 to 25 microns of the Orion Hot Core to see what we find. And so what we found so far is over 350 different unique lines. And we have identified 9 species and 2 isotopes with certainty. But we also have about 20 to 30 unidentified lines. And so we're still working on trying to figure out which species those lines belong to, because so far there's no comparable observations at these wavelengths. And so some species we found some species that show evidence for 2 different velocity components, namely acetylene, methane, CS, HCN. We also see SO2, we see water and silicon oxide in emission, and we see HNC. And so for this talk, I'm going to just focus on HCN, HNC, and H13CN. And these are 3 very complementary species. And just showing 2 examples of the XE spectra for these 3 species. And on the top, the HNC lines happen in a region with relatively low atmospheric interference. So they're much easier to analyze, whereas on the bottom, I should say that the flux that XEs is measuring is in blue, and in orange is the atmospheric model. And so the region where we see HCN and H13CN is a bit more difficult because we have to pull apart the molecular transitions from the atmospheric interference in this region. And so first, looking at HCN, which has been seen before in the mid-infrared in many studies. And it's a very important molecule. It traces very dense gas, and it's generally pretty much everywhere we look in the extragalactic, in the solar system, in our own galaxy. And it's a very important prebiotic molecule for DNA formation. And so this is one reason why we're interested in looking at hot cores, because they are part of the pathway between the cold molecular clouds that form stars and current planetary systems like our own, so we can understand the origins of these important molecules. And looking at the HCN, we can see 2 different separate velocity components. And we use the rotation diagram method to measure the total column density and the temperature of each. And so one component is similar to the outflow that's also coming from the radio source 1. And it's a bit cooler, denser, less dense. And then we have a hotter component with a different velocity that is, which is less dense. And this one we believe is much closer to the hot core itself because it's much hotter. And so these high resolution X's observations really allow us to focus on the heart of the hot core and probe it most deeply. And so, but of course, just looking at one species in isolation isn't so useful. And so this is where HNC and H13CN observations come into play. Because HCN and HNC, these two isomers, are created by similar pathways at low temperatures, but as the gas heats up, HNC gets depleted much more quickly. And similarly, looking at H13CN, we can gain a lot of information by looking at its ratio. We can get information about the carbon isotope ratios. And so these two species are cooler than HCN and also less abundant. And we only see the primary velocity component for these ones. And so by looking at the ratios, we do get a ratio of the carbon isotopes that's much lower than to be expected. And going through literature, we have seen some other similar low ratios in star-forming regions. And this also matches previous observations with acetylene. And so, but to explain this, we don't quite have a ready explanation for this discrepancy. So this will require more work, probably more observations to see how common this is. Whereas the ratio of the two isomers, HCN and HNC, match our expectations for this region, and we can use chemical modeling in order to find where this ratio is reached in the chemical modeling of the hot core, and we find it would take about 10 to 6 years for this ratio, which is much older than the explosive event. And so we confirmed that it's very likely that the hot core IRC2 formed prior to the explosion and likely around radio source I, and they got ripped apart. I think I don't have time for this one. And so just, so for future, we're working on looking at all these other species in the Orion Hot Core. We have a lot of acetylene data. We find that the isotope ratio for acetylene, we see it in both velocity components, is also similarly low. And we're working on analyzing and publishing the other species. So we're working on a large database paper. And finally, I just want to also highlight some work we're doing with some wonderful undergraduates. Jose Monzon is, he's analyzed the methane lines in Orion, and now he's also working on analyzing the water emission lines. And so he'll have a water paper coming out this year. Sierra Nabe is going through the SOFIA archives and just looking at all the different hot core data so that we can compare the hot cores and see what data has not been analyzed yet. And Jorge Vasquez has just recently joined us this month. And what he'll be working on is looking at the XE spectra and modifying it to see what our spectra would look like through JWST so that we can make predictions for future observations. And so just to conclude, we're looking at this hot core, we're building the inventory of it so we can find all these molecules and provide a roadmap for future observations for JWST, which will not be able to resolve individual transitions. And so we already found some interesting results, one ratio that's expected, one that's unexpected, and we're going to work on and soon publish the other species. But the paper on HNC, HCN, H13CN has come out in AppJ this month. And this science can really only be done by SOFIA XEs with complementary observations from TEXEs. And with that, I'd like to thank you very much for your attention, and I'm happy to answer your questions.
Excellent. Thank you, Sarah. Okay, so questions for Sarah. First one that we have comes from Roberto Carlos Pestaña Nobles.
Mhm.
Have you tried with machine learning algorithms to analyze and try to do prediction with your data?
So that's a really big question. I have thought about using machine learning. At the moment, the data we have is small enough that machine learning would be overkill because we can analyze it by hand without machine learning. The one feature that needs more sophisticated algorithms is the analysis of SO2 lines. And so it's probably not very obvious from this particular plot of SO2 I've grabbed, but with SO2, it's a very crowded species and the lines are really close together. And so for this one, I cannot analyze individual lines. What instead I'm doing is using a model of simulated spectra and using Markov chain Monte Carlo in order to find the best fit for the simulated spectra.
Okay, excellent. Our next question comes from, excuse me, from David Nesbitt. He says, Sarah, very interesting ideas. An explosive event 500 years ago seems like a blink of an eye in terms of astrochemical timescales. How is this timescale determined?
So I'm not an author of the original papers. So the details would be in the BAERI 2015 paper. But essentially the explosion came from a multi-body encounter. And so I believe, if I recall correctly, what they did was they're looking at the velocities of the gas, looking at velocities of the BN star, source I, and kind of just tracing the stars back to the beginning of it.
Okay, excellent. Other questions? We have a couple minutes. Otherwise, I'm going to have to start making jokes about all my XCs being with TechCs. Here we go. Tim has a question. Tim says, for SO2, are you considering the many different isotopologues that exist in a reasonable abundance?
Yeah, I think I did look at some of the isotopologues of SO2. I didn't find good evidence for them. But SO2 is so messy. I think it's worth looking at it again in more detail because it's our messiest species.
Yes, SO2 and phosphine are currently fighting in the atmosphere of Venus for our interpretation, so that makes a lot of sense.
Yeah.
Okay. Anyone else? All right, one last question from Professor Nesbitt. He says, as a follow-up, is there enough of a timeline for detection of this traceback to actually see the changes?
I think he has to clarify, or she has to clarify, traceback for.
Okay, maybe we can cycle back to that one.
Yeah, thanks, Ryan. Sarah, thank you very much. I'm talking about this tracing back in the BAERI paper to sort of a time of this explosion 500 years ago. I mean, is there any chance to actually test that by looking at some evolution of this gas flow over a finite time window? Clearly, 500 years ago, we didn't have any XCs and TechCs and so on and so forth. But is there a chance of actually really seeing dynamics in this explosive event over the course of the next 5 to 10 years?
That's a really interesting question. I have to admit, I don't have an answer because it has been a few months since I read that paper. But that's a really interesting thought. I mean, if it's true, it'd be really cool.
I'm just thinking, 500 years is just like a picosecond
It is.
to the universe. And so if we're really seeing things changing on sort of a human time scale, we could, in principle, have an opportunity to see dynamics in a completely novel way.
Yeah, I agree that it would be, I think, an interesting region to watch. And it's too bad we didn't have telescopes 500 years ago.
Yeah, at least not very good ones. But yes, thank you, Sarah. Very interesting.
Okay, so we have a few other questions. If we have some time at the end, we can cycle back to those for Sarah. So for now, let's thank Sarah for a wonderful presentation on the things that she's been doing. All right, so now we're going to transition into our second talk of today. But before I introduce Tim, I also want to mention, while we have the most people here, that the Astrochemistry Subdivision is currently soliciting nominations for our PhD award, which can, so those are open through the beginning of March, if I'm not mistaken. So if you have any students or former students or collaborators who have finished their PhD, whom you think are strong candidates, we encourage you to submit an application, and this can be done through the Astrochemistry website, through ACS Astrochemistry website. Okay, so now our next talk is going to be done by Tim Lee. So as a bit of a bio, Tim is currently a research scientist in the Space Science and Astrobiology Division at NASA Ames Research Center, where he was previously division chief for 10 years. He received a PhD in chemistry from the University of California, Berkeley, did his postdoc at Cambridge University, and began work at NASA Ames in 1988, becoming a civil servant in 1989. He is past chair of this subdivision, and his research interests include development of quantum chemistry methods with applications to astrochemistry, atmospheric chemistry, and molecular spectroscopy, including rotational, vibrational, row vibrational, and electronic spectroscopies. Today, Tim is going to be giving us a talk on the unsolved issue with out-of-plane bending frequencies for CC multiply bonded systems. So with that, I turn it over to you, Tim.
Thank you, Ryan. So let's see if I can share my screen now. This seemed to work okay the other day. Okay.
Looks great.
Great. Okay, everybody can see it? Okay. So this is more of a theoretical chemistry talk, but I'm going to show you a little bit why astrochemists should be interested in it. Let's see, that's not working. How do I page through? Great.
You might have to click the screen.
What do you mean click the screen? Oh, there we go. I see. Also, let me do this. Okay, so we can do that. Okay, so this talk is about carbon-carbon multiply bonded systems. And as you could see from Sarah's talk, over the quantum chemistry has been able to contribute to analyzing row vibrational and vibrational and data from laboratory experiments and astronomical observations for a number of years now because of the advances that have been made over the last 30 years. A recent study by our host group showed that with a composite scheme for computing quartic force fields, we could get fundamental vibrational frequencies to within 5.7 wave numbers and the B and C rotational constants to within 35 megahertz or 0.14%. So that's pretty good. However, there's one issue that has not been resolved in this over 30 years now, and that's out-of-plane bending harmonic frequencies of molecules containing carbon-carbon multiple bonds. And here's a little graphic to show that basically is benzene planar or is benzene bent, and that's what we're going to look at. And as a little enticement for the astrochemistry, here's a molecule that we've been trying to identify in astronomical environments for a long time, and also laboratory experiments. Protonated cyclopropanility, or cyclic C3H3+. This is what it looks like. This is the one we're interested in here. And if we, once we published that in 2011, Harold Leonard's group was able to do laboratory experiments where they were able to identify the molecule using a simulation of using our data from pGopher and shifting the band center just 0.55 wave numbers. You can see that our predictions came out very reliable. This is what quantum chemistry can do in the best scenarios, and that's what we're aiming for. However, in 1987, so this goes back a little ways, in 1987 and 1988, two groups independently, Ken Jordan's group and Fritz Schaefer's group, found that the harmonic frequencies, the out-of-plane harmonic frequencies for ethylene were too low computed at the TCISD levels in the first group and MP2 levels in the second group, and compared to experiment, and the other harmonic, the in-plane harmonic frequencies were actually quite reasonable. The symmetries of the two out-of-plane frequencies were B2G and B1U, where the B2G harmonic frequency had more of a, the effect was larger for that one than it was for the B1U mode. Both of these groups found, however, that at the Hartree-Fock level of theory, this was pre-DFT for the young people, at least in common quantum chemistry groups, the Hartree-Fock level of theory did not show this basis set dependency on the out-of-plane harmonic frequencies. And I'm gonna refer to a bunch of papers. This is sort of a review article, and I'm gonna refer to a bunch of papers. This review article came out in a special issue of Spectrochemica Active recently here, and I'm not going to look at or mention or give the details of all the papers I'm going to refer to, but you can find them in this review article here. Okay, the issue again then is that the harmonic, so I'm going to go through the different molecules now for which this has been found. Acetylene was the next molecule for which this issue was found in a 1988 study on the MP2 harmonic frequencies. And again, it was the bending frequencies, in this case, the pi G and pi U modes. Again, the pi G mode, the effect on the pi G mode was much larger than the effect on the pi U mode. This group looked at whether as you expanded the SPD space in the basis set, that the effect became larger, and that in fact the molecule, this harmonic frequencies became very low. They concluded that you needed to balance the basis set between saturation of the SPD space and inclusion of F functions at the as higher angle minimum functions, and in this case F functions. The effect for acetylene was much larger than that for ethylene, although keep in mind ethylene was the first molecule for which this was found. But it was later shown by Omloff and co-workers that acetylene could actually become bent at the MP2 level of theory if you completely saturate the SPD space with no F function. So it's not just the harmonic frequencies anymore, it's actually the equilibrium geometry of the molecule, which is quite interesting. Acetylene was further investigated by in a 1990 study. Well, in a 1990 study of HCCF, a similar issue was observed for the harmonic frequencies. It was suggested in this case that this was a general feature of linear molecules because an SPD basis set could be complete for a nonlinear geometries, but not for linear geometries. This was discounted in later studies because there's plenty of linear molecules that don't have carbon-carbon multiple bonds where this issue doesn't arise. And also this sort of neglects the fact that ethylene was the first molecule for which this was observed. The work on acetylene was expanded then in 1998 to include the CCSD parentheses T level of theory, and anharmonicities were computed. In this case, Dunning's correlation consistent basis sets and Omloff and Taylor's atomic natural orbital basis sets were used. The ANO basis sets in particular have much larger primitive sets. This is significant because the correlation consistent ANO basis sets are designed to be balanced with respect to saturation in the SPD space and inclusion of higher angular minimum functions, in this case going possibly up to H functions. The use of these basis sets minimized this erratic behavior of the pi G and pi U harmonic frequencies, but it did not eliminate it. it minimized it, but didn't eliminate it. And this was further shown in a 2010 paper where our composite scheme for computing quartic force fields was applied to acetylene. And it was found that the extrapolation to the one particle basis set limit failed due to the small inconsistencies that existed between the triple zeta, quadruple zeta, and 5Z basis sets. In this case, an R12 method was used to compute the quartic force field of acetylene, and it gave reasonable results. But again, this issue with the harmonic frequencies was not completely eliminated. It was just mitigated to some extent. Benzene probably has had the most work on it in this regard. The idea of balance was studied for benzene in a 1997 paper using several methods: Hartree-Fock, MP2, couple cluster, and DFT, specifically the B3 lip functional for DFT. This included many different basis sets, commonly used basis sets, including the correlation consistent and ANO basis sets. Several harmonic frequencies exhibited this basis set dependence, but especially the B2G omega-4 mode, even with the correlation consistent basis sets. The ANO 4321, which means 4S, 3P, 2D, 1F basis set, yielded similar errors for the out-of-plane and in-plane harmonic frequencies, but that was the only ANO basis set used. So we don't really know whether that all the ANO basis sets will will solve the problem, or if it's just mitigating it and minimizing the problem. Neither the Hartree-Fock nor DFT B3 lip methods showed any unusual basis set dependence on the out-of-plane harmonic frequencies. And it suggested that this issue was limited to electron correlation methods and wave function calculations. And that's the way it's been viewed for many years, up until a few years ago. And I'll get to that a little bit later. Based on other work that was unpublished by Almleff and co-workers, the fact that the ANO basis sets have the smallest basis set superposition energy by design, it was concluded that BSSE, or intramolecular BSSE in particular, was the problem. In a 2006 study, Moran and co-workers revisited the harmonic frequencies of benzene using MP2 and CISD with common basis sets, especially several variants of the Popel type basis sets 6311G. Again, the harmonic frequencies of the out-of-plane bending modes were erratic, and especially the B2G mode, omega-4, and they could actually get this mode to become imaginary. In other words, benzene becomes non-planar. They applied an intramolecular basis set incompleteness error diagnostic, and which suggested that the issue was an incompleteness in the one particle basis set. So this is similar to the basis set superposition energy. This diagnostic is a 2-electron property, which they asserted explained why Hartree-Fock and DFT methods do not exhibit this problem. And we'll talk more about that a little bit later. This diagnostic implied that we need a balance between saturation and inclusion of higher angular minimum functions, although still as we saw before, the ANO and correlation consistent basis sets still have some problems. The one thing that they did for the first time in that study was they applied this investigation to other arene type of systems, including in particular this one here, pyrene, where you've got a different atom in the ring, a heteroatom in the ring, nitrogen in this case. And they found that all of these arenes exhibit this problem, which is interesting. It's the first time that that was done. A little bit later, Astral et al. Investigated the harmonic frequencies of these same systems with the Hartree-Fock, DFT, MP2, and CISD methods with these various basis sets. But the difference is they included a counterpoise correction to eliminate this intramolecular BSSE. They showed that the MP2 and CISD all had imaginary frequencies removed when they included the counterpoise correction, but some of the out-of-plane bending frequencies were still too low. Especially the omega-4 B2G mode. Again, that's the mode for benzene that is the most affected. They showed that Hartree-Fock and DFT were little affected by the counterpoise correction, again suggesting that these methods are this problem does not affect those particular methods, or that they're immune to this problem. They did note, interestingly, that in 2000, in a 2003 study, Jensen found that the omega-4 harmonic frequency of benzene becomes imaginary with the blip functional, with an unusual, very small, although augmented with diffuse functions, uncontracted SPD basis set. So that was the first indication that maybe DFT is going to have an issue with these types of problems as well. In 2017, Samla and Jordan revisited the harmonic frequencies of benzene at the MP2 level using correlation consistent basis sets, using the triple zeta, augmented triple zeta and augmented double zeta basis sets. They found that the harmonic frequency using the triple zeta basis set was actually imaginary, but at the double zeta basis set, it was not. From this, they concluded that BSSC was not the issue because the basis set superposition error should be larger for the double zeta basis set than it is to the triple zeta basis set. After looking at their calculations, they concluded that there was a near linear dependence in the basis set after examining the eigenvalues of the overlap matrix. And once they pruned the molecular basis set based on the eigenfunctions that correspond to the small eigenvalues of the overlap matrix, they could get the omega-4 harmonic frequency to become real again, and also to come into alignment with experiment once they pruned enough functions. However, in talking with Ken Jordan, I found that they had no convergence issues with the Hartree-Fock wave function. This is a telltale sign that linear dependencies are not a significant issue. They did show, though, that intramolecular BSSC was not the issue, and that balanced basis sets like correlation consistent still yield erratic behavior for benzene. So I want to go back to ethylene again because that was the first molecule for which this problem was found. Martin et al. Reported a Cortic force field for ethylene at the CCSD parentheses T level using the DZ, the correlation consistent DZ and triple zeta basis sets. The two out-of-plane bending harmonic frequencies for ethylene show that there's a little bit of basis sensitivity relative to the in-plane vibrational modes. And this, again, is especially true for omega-8 to B2G mode, similar to what was found in the earlier studies and the original studies in 87 and 88. While the error that's going to exist for these out-of-plane bending frequencies is larger than usually expected for this level of theory, it's larger than what we're used to finding in this level of theory, the magnitude of the errors for ethylene are much smaller than those for either acetylene or benzene. Really, acetylene and benzene are much more significantly affected by this issue. And just to be complete, there was a 2018 study where they have probably the most complete set of harmonic frequencies of ethylene with various Popel type basis sets and correlation consistent basis sets. But their findings are essentially consistent with what was found earlier. So what do we know then from these studies? We know that this occurs for carbon-carbon multiply bonded systems using correlated wave function methods. Other than that one exception, Hartree-Fock and DFT seem to be immune from this problem. And then, of course, the basis set that was used in that one blip calculation was quite unusual. It's not one that anyone would normally use. This suggests that this is somehow due to a one particle and n particle basis set coupling issue. And the various studies have suggested that you need to have a balance between saturation and inclusion of higher angular minimum functions, that there might be intramolecular BSSC or a basis set incompleteness error, or that there's near linear dependencies in the basis set. But what all of these have in common is that they're changing the one particle basis set in some way, again, which suggests that this is a coupling between a one particle and n particle basis set somehow. But in this case, they would modify the basis set until agreement with the experiment is achieved. But the trouble is with that approach is that you can't ever be confident in predictions. So you don't know, one approach for one molecule is not going to work for another molecule. And so this means that the method becomes less predictive if that's the case. So let's go on to the next one. What else do we know? We know that the mode that is most affected in all of these three molecules is always one that retains inversion symmetry, which is interesting. But we know that inversion symmetry is not a requirement, as demonstrated by Moran et al. When they examined several A-ring type molecules, including one with a heteroatom in the ring, pyridine, which exhibited this problem. So while this is an interesting observation, the one that most affected is one retains inversion symmetry. That's not a requirement. We also know that benzene is much more significantly affected than acetylene, which is much more affected than ethylene. And we know that, what else do we know? We know that it doesn't, this is perhaps the most, the point here is perhaps the one that's the most irritating, the most misunderstanding, the difficult problem to understand in this. It doesn't affect all carbon-carbon multiply bonded systems. Why, and how do we know that? We know that from doing our course field studies on cyclopropanility, protonated cyclopropanility, the linear version of C3H3+, and a nitrogen substitute version of the protonated cyclopropanility. None of these molecules exhibit this problem. So this also suggests that it's not simply due to basis set superposition error or linear dependencies, because otherwise these molecules should exhibit the problem as well. So what's the path forward? The out-of-plane Binnian harmonic frequency problem appears to involve some coupling between these, the n-particle and one-particle basis sets. All of the solutions that have been arrived at involve somehow modifying the one-particle basis set. But the problem is they modify it until it agrees with experiment, but we want to be able to do predictions. So that's not really an acceptable approach. And we really don't understand why the problem exists. None of the proposed issues really resolve what the problem is. So one possible solution is to just use A and O basis sets, especially where the contraction coefficients might be obtained from multiple atomic electronic states. The Almuth and Taylor basis sets don't do that, I don't think, but I think the Lund A and O basis sets do use multiple atomic electronic states in their contraction coefficients. That would be a quite expensive approach though. Another possible solution is to treat the out-of-plane Binnian harmonic frequencies separately from the in-plane modes, which has been tried in a limited case, but that a robust method must be developed in order to do that. That's going to work for all molecules. But one of the most important things is that whenever people have looked at this issue, they've applied it like the BSI diagnostic or use of counterpoise corrections to these systems, but they haven't, what they haven't done is they haven't applied these diagnostic or use of counterpoise corrections to other systems that don't exhibit this problem, like cyclopropanility. And it would be interesting to do that. We're going to have to be able to understand, if we understand what's going on with acetylene and benzene, we need to be able to show that it's not, the problem is not, why it doesn't exist for cyclopropanility in molecules like that. So I'm not quite finished yet. I want to move now into larger systems and also talk about DFT. We've sort of said that DFT is immune to this. So some of you may know, but I've been involved with Cameron Mackey and Xander Thielens et al. Working on the anharmonic calculations for PAH molecules. And here's a few of the systems we've looked at. And ultimately, in the end, what we're interested in doing is determining the fully anharmonic cascade spectrum of PAH molecules in order to compare directly with astronomical observations. This is something that will be very useful in analyzing JWST data. And in this regard, as I indicated, DFT seems to be immune from this problem, except in 2016, there was a paper that looked at a family of cornene PAH molecules. When I say family, I mean larger and larger cornene molecules. And they showed that many imaginary frequencies appear for the out-of-plane harmonic frequencies. And I also will note that he pointed out that cornene itself was found to have imaginary frequencies at various DFT levels in a 2008 and 2010 studies, which weren't the main purpose of those studies, which is why we probably missed those. He used Hartree-Fock MP2 and DFT with several functionals, including B3-LIP, several commonly used basis sets, but all small basis sets because these are quite large molecules. He found several of these combinations yield at least one, and in some cases many imaginary harmonic frequencies. And he found also at the Hartree-Fock level, some appeared to yield imaginary harmonic frequencies. But looking at his paper carefully, these appear to be due to linear dependencies, and I'll mention that again in a second. The linear dependencies, however, do not explain what's going on with the DFT results. Then later in 2016, Bauschlicker studied the N=4 and N=5 cornene molecules and found imaginary out-of-plane harmonic frequencies using BP86 and B3-lip functionals with various basis sets, but small basis sets. He also studied using larger grids. He studied 5D versus 6D functions in the basis set. And he also used the default and Gaussian for eliminating linear dependencies for molecules. Once these molecules get big enough like this, linear dependencies are going to crop up. So it makes sense to do that. And Gaussian has an automated way of doing this. And he found no situations where Hartree-Fock yielded imaginary frequencies. So again, Hartree-Fock does not seem to be subject to this problem. And the problem, I think, in the previous study that I mentioned was probably mainly due to linear dependencies. Neither the grid size nor the 5D versus 6D made a difference in these imaginary frequencies. He did also examine whether different electronic states of the carbon atom as you moved along the harmonic frequency might explain what was going on, but he found no evidence to suggest this. The main purpose of both these studies on the cornene family of molecules, though, was to find a small SPD basis set which yielded reasonable harmonic frequencies for very large PA molecules. So they played with the value of the D exponent and could get reasonable values at some point, but a D exponent for one molecule did not work for a different molecule in the same family. So that's not, again, that's not a viable solution. One of the questions then is this related to the wave function out-of-plane bending issue for small molecules? Karadakov thinks maybe, but Bauschlicker thinks not. So it's not really clear whether that's the case. So conclusions: in spite of the many great successes of quantum chemistry in computing highly accurate fundamental vibrational frequencies and low vibrational spectroscopic constants over the last 30 years, one significant issue remains unresolved: the out-of-plane bending harmonic frequency problem for some, emphasize some, carbon-carbon multiply bonded systems. The many possible explanations of this problem all involve modifying the basis set in some way, but none of these is consistent with all of the data, and none eliminate the problem, they just minimize it. Any robust understanding and solution to this problem must, why some carbon-carbon molecules exhibit this problem, any robust must explain why some carbon-carbon molecules exhibit this problem and others do not. And it must also not require the use of experimental data to arrive at a solution. In other words, we want to be able to make our predictions, and we want to know that those predictions are reliable and accurate. The recent findings for the PA molecules using various DFT functionals, it's not clear whether they're related. And it's difficult to say for certain whether it's related because we don't really understand what's going on with acetylene, ethylene, and benzene. And again, I mentioned the review article here. That's where people can find more of the details. I obviously couldn't include them all here. So, and all of the references that I've mentioned in the talk today. I want to thank our funding. These are the funding group agencies, or it's all NASA, but these are the funding programs that we've had within our group. And I want to especially thank the people who have helped work with me over the years on computing anharmonicities for large molecules and also for small molecules. And in particular, there's Ryan there. All of these people have worked on this in some way over the years. There's Ryan, there's Partho, Jin Chuan, Natalia Anestroza, and thank you for your time.
All right, thank you, Tim. So we have a couple of questions that have already come in. The first comes from Ann McCoy. It says, she says, the talk focused on trends in harmonic frequencies. I was wondering if this behavior has been explored for anharmonic frequencies. While I'd expect that the basis set dependence should affect both, when you first mentioned the discrepancies, my first thought was that it could be related to the fact that the potential is flat, large quartic terms, along these coordinates. And that could be related to sensitivities of harmonic frequencies to computational details.
You may know that Ryan and I, with some other people, looked at some anharmonic calculations of cyclopropanility in particular in the last few years, where this appeared to be the issue, but it didn't show up at the harmonic frequency level or at the geometry level. And in fact, we were able to show with subsequent studies that the problem was in computing the quartic force constants. We needed to make either larger steps or use more robust linear, more robust method to solve the linear least squares fit problem. So at least as far as, I'm not going to say that for sure that this wouldn't appear in the cubic or quartic force constants, but I focused today really more on the geometry and harmonic frequencies. And I guess it's reasonable to expect that it might show up in higher levels. But if you don't solve the problem for the geometry and harmonic frequencies, then we won't necessarily know about the cubic and quartic. The one example we have, as I said, is we were able to resolve in other ways.
Our next question comes from Stephen Klippenstein. Do these problems also exist for F12 methods with F12 basis sets?
I would think that, yes, I think the short answer to that is going to be yes, they will exist. I think the F12 methods, like using reasonable basis sets, the correlation consistent basis sets, and ANO basis sets, they will minimize the problem, but I think they're still going to exist.
Yep, I would second that. Okay, so our next question is from Zayun Tang. He says, can you comment on the difference between anharmonic calculation and ab initio molecular dynamics for getting IR spectra? Which approach is better for PAHs when using the same functional and basis set? Well, I've got a lot more experience computing anharmonic spectra using a quartic force field as opposed to molecular dynamics. But I do have a little bit of experience using the molecular dynamics, which was not a good experience, frankly. I think it's really difficult to get consistent, to get a spectrum using molecular dynamics that is consistent with the observations. Whereas if you go back and look at the PA studies that we did with Cameron Mackey, we were able to get spectra that agreed pretty well with high resolution laboratory experiments. Our next question is from Kirk Peterson. If this is a coupling between one particle and n-particle expansions, doing an accurate CBS extrapolation should be guaranteed to account for this. How about 5Z, 6Z CBS study of acetylene? Would be an interesting thing to try that. But if it were really just that, then I think that you would see it again with cyclopropanility, and we don't. So in fact, we don't see any inkling of a problem with cyclopropanility or C3H3 plus or the other most of those other molecules. So, but that would be something to try. I haven't tried that myself. I haven't done like a 5Z, 6Z or extrapolation. That we have gone up through 5Z. We haven't tried 6Z though. All right, our next question comes from Joseph Ortiz. Have correlations of problematic frequencies with eigenvalues of HF stability matrices been considered? Can you repeat that question, please? Sure. Have correlations of problematic frequencies with eigenvalues of HF stability matrices been considered?
Not that I'm aware of. It's possible if anyone investigated that, I would have thought it would be the Moran paper, Moran et al., which came out of Fritz Schaefer's group. So I would think that maybe they did, but I'm not aware of anyone else having looked at Hartree-Fock instability indices for these.
Okay, our next question comes from Michio Okamura. Are there problems in the dipole function and intensities?
That's a good question. I'm sure there's going to be problems in the intensities when the modes become imaginary. In terms of computing the dipole moment function, well, again, if the molecule actually becomes bent, then the dipole moment's going to be wrong. In most of these studies, people didn't compute intensities. So I don't know, for sure the answer, but I think that that's quite likely to be the case, especially if it gets bad enough that the molecule becomes bent or non-planar.
All right, our next question is from Nathan DeYonker. He says, why does this problem manifest for CC double bond out of plane bends for tetraatomics and beyond, but doesn't show up with X CC triatomic bends?
I'm not sure I understand the question. Do you mean by like you've got a X being something like another heavy atom? I mean, it did show up in HCCF, but in that case, the fluorine is really replacing a hydrogen.
But would it show up with like CCF or C2H?
And I don't know if people have really investigated that, but it did show up for HCCF. But I think what Nathan is really asking though is, does it show up for something like where you've got carbon, 3 carbons in a row and things like that? I haven't seen anyone, I haven't seen papers where people have shown that, but and then again, they may not have investigated that. One thing I really didn't talk about too much here is it's sort of difficult. You do one calculation, you do a quartic force field, one level of theory, and you think everything's fine. If the molecule isn't non-planar or become bent, then you think everything's fine, and so you don't know that there's an issue. The only way I can think of to make sure that you don't have an issue is to do like the DZ, TZ, QZ, 5Z basis sets, or maybe not the DZ, the TZ, QZ, 5Z basis sets, the correlation consistent basis sets, and see what the basis set sensitivity is on those out of plane vibrations. And if you see that the basis set sensitivity is larger than it is for the in-plane modes, then that's an indication that you have this issue. And as the molecules get bigger and bigger, it's possible that people don't do multiple basis sets like that in order to determine whether this issue exists. So.
Okay, so we're getting onto our 2 o'clock hour. There were a couple of clarifications. Maybe we can talk about some of those offline. And there was a mention of the ExoMol project as well. But we are out of time for today. So again, I want to say thank you to our 2 speakers. Thank you to all of our attendees. Also, please remember that if you have any graduate students within the past 2 years who are graduated that might be outstanding candidates for our Astrochemistry Dissertation Award, please feel free to submit applications to that. If you have any other questions, feel free to let us know. Otherwise, we look forward to seeing you in a month. Thank you again.
Thank you.
Thank you.